we are going to see active low pass filter now. So far we had seen passive low pass filter. So in the active low pass filter, what we are doing, so it means it's the combination of standard inverting or non-inverting operational amplifier together with the basic RC low pass passive filter. So here you can see, so this part is called a traditional passive low pass filter. You can see just one resistor and one capacitor. This is the design we had seen so far. So in this active, okay, I think it's in the previous slides. Okay, this is the normal low pass filter, passive low pass filter. We are just adding either inverting or non-inverting operational amplifier in the series or together with this LPF. Then it becomes active low pass filter. So what is the difference between this circuit and this circuit? So here you can see, here we are using operational amplifier just like a voltage follower or a buffer, because we do not have any input resistor or feedback resistor. Okay, so here we will see why this circuit got modified into this circuit. So in this figure, you can see this is a simple non-inverting amplifier. It means we are giving the input to this positive input terminal, non-inverting input terminal. It acts as a buffer. It means the voltage gain of this buffer is equal to 1. So whatever the input you are applying to this operational amplifier, it will not be amplified at the output. You will get the same at the output. But as I told you in the previous, just before our break, we get two advantages by introducing this operational amplifier. One is we avoid the loading effect. Second one is it amplify the input signal. So if you want to amplify, then you have to move to the circuit. Instead of having the unity gain, you are going to add the input resistor and feedback resistor. So here you can see this is the feedback resistor and this is the other resistor, input resistor. Then you know the formula of the output formula of this operational amplifier. So here the formula or the gain of the non-inverting operational amplifier is 1 plus RF divided by R1. I think in the lab and also in the assignments, I had seen some students, they mixed up between this RF and R1. So they put R1 in the top and RF in the bottom. So that is not correct. You always remember the feedback resistor is coming in the top of the equation. So 1 plus, in this case, R3 is the feedback and the input is R2. So if you change the resistor position, then the value, what you will get at the output is totally different. So do not get confused. And you better write down the formulas when we go through each filter design, because at the end, there are so many filters and you may get confused between the output formula, especially the output formula. Mostly cutoff frequency is going to be the same. Okay, so now you know the output or the gain of this operational amplifier. And now we are, because since here the unity gain, we just changed and added these resistors, and this low pass filter is the same. So this is the complete first order active low pass filter. So the circuit, the final design of this active low pass filter will look like this. So here the gain of the non-inverting op amp is 1 plus RF divided by R1. So in this case, R3 divided by R2. And we know the cutoff frequency of this simple passive low pass filter, FC is equal to 1 divided by 2 pi RC. So this is no change and no change. So now we are talking about this as a single circuit. So the gain of the complete active low pass filter is equal to, the gain is what? That is a transfer function. V out divided by V in is equal to AF. AF is nothing but the gain of this section of the entire circuit divided by square root of 1 plus f divided by fc whole square. So this is the voltage gain formula for active low pass filter. So this is different from passive low pass filter gain. So here you may ask, what is this f? What is this fc? So f is the frequency of the input signal and fc is the cutoff frequency. So of course the unit is always hertz for frequencies. It can be kilohertz or megahertz, but it's a hertz. So just try to remember in this slide, I just want to highlight this formula, these three formulas. This one you already know, and this one you already know. This is the voltage gain of this entire circuit. So now the gain of the complete active low pass filter, we know that. So now we can have three different cases. This is the case 1, and this is the case 2, and this is the case 3. So how can we classify these devices, or how can we differentiate these cases? Here you can see the first case, f is less than fc. So we know f means that is the frequency of the input signal. So this is the, you are applying the input here, V in. So this is the frequency of this input signal, and fc is the cutoff frequency, we know that. So when we apply the input signal, its frequency, when it's less than the cutoff frequency, then V out is divided by V in is equal to AF. So here this entire circuit will act as a just a non-inverting amplifier. So here I think you can see here the text. So this one, the first condition is F is less than FC. So here the active low pass filter has a constant gain of AF from 0 hertz to the high frequency cutoff point. So, and this is the second case. Here F is equal to FC. So applied input signal frequency is equal to the cutoff frequency. At the time, what's happening? V out divided by V in, that is the gain, is equal to AF divided by square root of 2. That is this value, that is the 0.707 AF. And the third case is F is greater than FC. So here the gain is less than AF. So now I think you can try to relate this to the frequency response. So when we make the frequency response, or maybe we can just go back to the frequency response. So here you see, this is what I mentioned here, 0.707 AF. AF is the gain. So that is V out divided by V in. So here we will get the minus 3 dB in terms of dB. So here we get this cutoff frequency, and whenever you apply the input signal, its frequency can be less than this FC value, or it can be equal to the FC value, or it can be greater than this FC value, this side. So that is what you have to recall the graph here. So whenever F is less than FC, then the gain is equal to actually the gain of this operational amplifier. So you can amplify if you want the input signal value. For example, it passes the low frequencies. F is less than FC means that is the low frequency. It's the low frequency you can get at the output. Normally, if you just only use this one, the value magnitude will be less. Since you are using the operational amplifier, it's depending upon the gain of the operational amplifier, the signal will be amplified at the output. So that is what the meaning of the case 1. The case 2, when F is equal to FC, then the graph start to fall down. The graph will just start to, if it's a low frequency, then it will start to fall down. So then that is 0.707 AF, that is the minus 3 dB level. And at high frequencies, so what we want at the high frequency, we want the output should go to 0 because this is a low pass filter. So V out divided by V in is less than AF. So it will just go down more and more, and then it will reach 0. So after FC, after the cutoff frequency, it decreases at a constant rate as the frequency increases. So when you increase the frequency, the output or the gain decreases linearly. That is when the frequency is increased tenfold, that is the 1 decade, the voltage gain is divided by 10. So this is the definition of what I said, like a minus 20 dB per decade, the roll-off rate. This is 20 dB per decade. Okay, so in other words, the gain decreases 20 dB each time the frequency is increased by 10. So please try to connect this sentence and what I said here. So when dealing with filter circuits, the magnitude of the passband gain. So this is the passband gain of the circuit is generally expressed in terms of decibel. This is the, it's actually as a function of the voltage gain. So the formula is here, that is the gain calculation formula. AV is equal to 20 log of V out divided by V in, base is 10. So that is why when you increase the order of the filter, then you will increase the roll-off time. So instead of this 20, then it's going to be so n times the 20 dB. This is the standard value. So how can we calculate the 20 dB? So here you can see. So if it's a second order filter, then it will be minus 2 times minus 20, that is going to be minus 40 dB. Remember here, we do not have the minus because we are applying the input to this positive terminal. So there is no phase difference with respect to input. That is why here we don't have positive. So, but the fall down, it will be 20 dB per decade, the same. So n times 20 dB per decade. If you use the second order filter, then it will be 2 times 20 dB. So that is going to be plus 40 dB. Anyway, the principle is the same. The curve will fall down towards 0, either slower or it's faster. So now there is one small problem, active low pass filter problem. So this is the question. Design a non-inverting active low pass filter circuit that has a gain of 10 at low frequencies. A high frequency cutoff or corner frequency is 159 Hertz and the input impedance is 10 kilo ohm. So I had given the solution already. So I want you to solve this problem. You can also refer the solution if you need a help. The solution is step by step. You can just remember the formula and then you apply the values and you will get the correct values.